So this will be our last video for the time being on limits at infinity. But in this case, we're going to consider what happens when we have radicals, or also if we have rational exponents. So let's just look at an example here, and we'll try to figure out how we do this. Now, in the last video, we dealt with an example where what we could oftentimes do is we can really just consider the lead coefficients. And remember, the lead coefficients aren't always going to be the first coefficients, but they're going to be the coefficients that have exponents with the highest power. In this case, it will be the one that's the first one, and it's going to be 5/3. And it turns out that we actually can just consider those lead terms for simplification purposes. So this will, in fact, be the same as the limit as x approaches infinity of 10x to the 5/3 over 5x to the 5/3. So that part actually still stays the same, even if you don't have polynomials. So in this particular example, we're going to have 10 over 5, and then you can think of these guys just canceling if you want. That's an easy way to think about this, and your limit will be 2. So this works. And really, as long as you're taking a limit as x approaches positive infinity, this is going to work pretty much the same as it did when we dealt with integer exponents when these were actually polynomials. But we have to be a little bit more careful when we deal with something that occurs when x approaches negative infinity. And the reason, of course, is because we have to remember that when we have rational exponents, really what we're doing is we're taking the mth power and then we're taking the nth root. Okay? And the thing to remember here is that if you want to take the nth root of something that is negative, okay, and n is even, this is going to be complex. It's not going to be a real number. And that's going to end up being just a little bit problematic because as x approaches negative infinity, we imagine that we are plugging in large negative numbers into this. And where we have to be specifically careful is that any time in the problem we have something where we have basically a fraction here and our n is even, after we do some simplification, we're going to run into that issue of it being undefined. So this isn't just a matter of looking at the lead term here, but we have to notice that we've got a 1/2, and that denominator is even. And even if it's in another term, it can be in the first term, this is going to result in this limit not existing. Because it's not even defined for any negative number. Imagine if you plug in -1, -2, -3. You're taking the square root of negative numbers here. It doesn't work out. Now, if we don't have that issue, we just have odd roots like this, then we can treat it like any other problem, and this will also just so happen to be 2, like it was in the top one. So just to consider the graphs of these things, if we look at our first function, which is the function that's associated with these two, notice that we don't have anything over in the negative values. We do have the limit of 2 here, but we've got nothing over here. But in this bottom function, if we just get rid of this 1/2 and we replace it with the 2x to the first, now we do have information over here, and both the positive infinite limit and the negative infinite limit are going to be the same. So there's one other type of example I want to look at, and that's going to be an example that looks like this. And of course, the corresponding negative one. In most cases, when we took a limit at infinity, as long as it wasn't an infinite limit, the plus infinity limit and the minus infinity limit were oftentimes the same. But there are cases such as this one where these two limits are actually going to be different and they are going to be real numbers. So let's see how that can possibly happen. So again, we're dealing with something like this. We have a root here. And just like before, as a rule of thumb, we really can ignore everything except the lead term. Okay, so in both of these examples, when we take the limit as x approaches infinity or negative infinity, really I can just consider this as the same as the limit of 12x, because that's the highest power of x in the numerator, over the square root of 16x squared. And this term, and this term can disappear. And this will actually be quite helpful because now we can simplify 16x squared. But this is where we have to be careful, because if we take the square root of 16x squared, this is, of course, the square root of 16 times the square root of x squared, and the square root of 16 is 4. That's fine, but the square root of x squared is not x. Oftentimes we simplify it as x, but that assumes that x is greater than 0. This is actually going to be the absolute value of x. And think about why this is the case. If I take the square root of 3 squared, for example, that's going to be the square root of 9, which is going to be 3. And if I take the square root of something negative, well, negative 3 times negative 3 is also 9. And the square root of 9 is 3. So regardless of whether you start with a negative or a positive number here, you're going to end up with a positive number. So the square root of x squared is the same thing as the absolute value of x. And this is where, as I said before, things get interesting. So this is actually going to be the limit as x approaches infinity of 12x over 4 absolute value of x. And if we simplify this, this is just going to be 3, the limit as x approaches infinity of x over radical x. And just as a reminder, we've kind of dealt with x over radical x as a function by itself, which is actually the same thing as absolute value of x over x, is going to be this function that's going to be positive 1 when you're greater than 0, and it's going to be negative 1 when you're less than 0. So it's going to be negative 1 here. It's going to be positive 1 here. So as x approaches infinity, this thing is just going to be 3 times positive 1, or 3. When we deal with this bottom example here, all of the math is the same. This is going to simplify as the limit as x approaches negative infinity of, and we can just say 12 times, or not 12 over 4, but that's going to be 3 x over radical x, or x over the absolute value of x. Except this time, because we're looking at larger and larger negative numbers, that's actually going to correspond to negative 1. So this is going to be 3 times negative 1, or negative 3. So the top limit is positive 3, the bottom limit is negative 3. And if we consider the graphs of both of these functions, we'll see that the horizontal asymptote as x approaches infinity is y equals 3, and as x approaches negative infinity, it's going to be y equals negative 3. So this is that special case where both of these limits exist, but they are different. And again, oftentimes this happens when you're taking the square root or any nth root of some x to an even power in it. And that's how we do problems like this. Again, as always, I hope that you found this video helpful, and take care.